It's time to look at WebGL textures. In this video, we'll try to get a simple texture working on our canvas with as little code as possible. In our first attempt, and just for simplicity, we'll try using an array of color values rather than an actual external image. We'll see how easy it is to add a texture to your shader code. We'll learn about UV texture coordinates and samplers. And once we've got all that working, we'll see what we need to do to get an actual external image showing up on our canvas. We'll explore the three main forms of the function textImage2D to see what they do and how to use them. And last, we'll look at sampler uniforms, texture units, and what you need to do to load and render multiple texture images with a single draw call. In two videos to come soon, we'll go onward a little bit and look at MIP maps and how to start working with texture atlases, also known as sprite maps. So look forward to those. Before we get going, if you're new to WebGL, I feel like a warning is in order. Understanding how to load and display textures in your WebGL programs is not an advanced skill at all. If you keep digging, it can be, but just getting textures into your primitives is definitely not. But to get the most out of this video, I think that you probably need to have a really solid understanding of more basic concepts like attributes and uniforms. And bonus points if you know what WebGL objects and targets are. It's not absolutely essential to have these things, but without them, I think textures can come across as way more complicated than they really are. So as you watch this, if you feel a little bit shaky on some of the code that you see here, maybe just hit pause and brush up on these things first, and then come back. I've got videos that might help. Link in the description. So, to get started, first we have to prepare our application. Like we've done before in this series, we're going to return to our Hello World example. This uses point primitives, which are no good to us now. We need a primitive that has an area. A mesh would be nice, but all we really need is just a triangle. If you watched my video on attributes, then you already know how to do this. So let's just do it. Okay, now we're ready for textures. I think it's easiest if we start with our fragment shader, start at the end and work our way backwards to fill in all the missing pieces. So here's the final line of shader code that literally powers everything. In a fragment shader, instead of setting our output color to red, like we did before, we're using the built-in texture function to calculate our color value. It takes two arguments. The first argument is a sampler variable. And in our case today, we're using a sampler 2D. You can sort of think of a sampler as an intelligent wrapper for an image. It's able to quickly decide what color is found at a certain very exact coordinate. If that coordinate is somewhere between two or more pixels, the shader will figure out the best way to blend those pixels into the most correct color value. Your GPU is able to store lots of samplers, and your shader is able to use several samplers at once. So this sampler variable is used to identify the sampler that you want to use. And the second argument is a texture coordinate. You might think of this as an XY point on your source image. Because it's convention, I'm going to call these coordinates with the names U and V throughout this video. You may also hear them called S and T in certain situations. Now, there is a very nuanced difference between UV and ST coordinates, but I'm going to completely ignore this in this video. I think that it overcomplicates things way too much for beginners, and I really recommend not getting distracted by it for now, because it really doesn't matter. Where do these values come from? The sampler 2D will arrive as a uniform directly from our JavaScript, but the UV texture coordinates will be attributes. Hopefully you already know only vertex shaders get attributes in WebGL, not fragment shaders. So these values must come in to the vertex shader and send across to the fragment shader as a varying. UVs for a 2D texture have just two components, a U and a V, so it will be a vec2. If any of this sounds confusing, you can watch a couple of my previous videos. Attributes Part 1 go into writing exactly this kind of code, and Part 2 goes into more detail on the vertex attrib pointer function if you want to learn everything about that. And that's all our shader code needs. All that's left to do now is provide a vec2 attribute and a sampler2d uniform for our JavaScript, and we're good to go. In our JavaScript, why don't we start with the UV coordinates first? UV coordinates are vertex attributes, similar to our vertex positions. For performance reasons, we really should keep this in our existing vertex array, but let's keep this as simple as possible and put these into their own buffer. Our UV data doesn't exist, so we need to create a new float32 array, but what data do we put in there? And more fundamentally, what is a texture coordinate? Okay, let's take a second to sort this out. So imagine that you have a cube like this that you want to render with a texture. It's a cube with 6 faces. 6 faces means 12 triangles that need a texture. Now let's imagine that this is the image that you want to use for your cube texture. The image size and dimensions don't matter. How the individual sides are laid out doesn't matter either. The question is, how do you get your 12 triangles to pick up exactly the correct parts of this image so that you're displaying something like this? To begin, let's pick one of the triangles in our cube object. Now, take a look at the texture image and decide what parts of that image should go into that triangle. There are several candidates you could choose from, but let's choose this one. If we change our object a bit, for example, compressing it along one axis, but keep all our edges lined up like they were before, how would that affect the triangle on our texture image? I hope it's pretty obvious that it doesn't affect things at all. The texture coordinates will remain the same. The rendered image may look a little squished in one direction, and this is really only obvious in a pixelated texture image like this one, but the bottom line is that to keep our edges lined up, our texture coordinates haven't changed at all. So really our job isn't just to figure out the exact positions in 3D space for the vertices A, B, and C, but also to find the corresponding UV positions on our texture image. The last sort of head scratcher for newcomers is that these UV coordinates aren't measured in rows and columns or pixel coordinates, but rather in floating point numbers between 0 and 1. 0, 0 would be at the bottom left, and 1, 1 would be at the top right. So our final position and UV coordinates would look something like this. Okay, so let's go back to our simple triangle and decide what our UV coordinates are and finish off our vertex buffer definition. Our last job is to create our WebGL texture object. This is the second kind of WebGL object we've encountered in this series. Our first was a buffer object. You can tell it's a WebGL object because it has a create function and a bind function, and also a delete function that we've not used yet in this series. So the first 2 lines here should seem completely familiar to you. Note that we're binding to a new kind of target here. With buffers, we've bound to array buffer for vertex data and element array buffer for index data. The target we'll bind to here is texture2D. It's the simplest, and it's what you use for simple, basic, flat 2D dimensional images. And now to populate the object with image data, instead of calling buffer data like we would with buffers, we call textImage2D. This function becomes available only when you bind to texture2D, which we've done, so we can use that here. We have to specify some kind of image data. In a minute, we'll try using an external image file, but for now, let's just specify some hard-coded random RGB values. I've created some here. And we're done. Almost. One last weird wrinkle we have to iron out. One of my next videos will be on a feature called MIP maps. I won't go into what these are here, but what you need to know now is this. WebGL by default expects you to be using MIP maps, and we're not here. So you basically have 2 options to make your program work. You can give WebGL the MIP maps it wants, or you can override this default setting so that it doesn't need MIP maps at all. Which one you choose really depends on what you're doing. If you want to use MIP maps, the easiest thing you can do is just have WebGL generate them for you using this command. And if you don't want to use MIP maps, you can change this setting. What's it doing? Well, it changes the minification filter function. Basically, it's telling WebGL how to use the sampler as the image gets smaller and smaller and smaller in your canvas. If you do go this route, there are only two functions you can choose from, either linear or nearest. By the way, by default, this function is set to nearest mipmap linear. See how it explicitly expects you to be using mipmaps? That's why you either have to provide mipmaps or change this setting. That's all it is. In our case here, we aren't even using a minification function. Our image data is 4 by 4 pixels in size, and our triangle is much bigger than that. But there is a magnification function, and in our case, this will work for us. There are only two options here, linear and nearest. Nearest will snap to the closest pixel in our source image, giving it a very pixelated look. Linear will smoothly transition between each pixel in our source image, giving it a very smooth, though sometimes very blurry look. And do you know what this triangle needs? It needs an adorable kitten. I've got one here we can use. But we have one huge problem. All of our code here, and so far in this series, has been completely linear and synchronous. But loading an image in JavaScript is an asynchronous task, meaning we can request an image, but if we want to use that image for anything, like using it in a texture, we have to wait until it's finished loading. Now, this isn't a tutorial in image loading. I like using async await, so that's what I'm going to do here, but I want you to please do this the way that you're used to. Await can only be used in a function that's been declared with the async keyword, so we're going to have to move some of this code into this new function, including anything that depends on the image and our first draw call. Now for my load image function. Await expects a promise, so that's what I'm going to write here. I've created a new HTML image element object. I'll attach an event listener that will return the image element when it's finished loading. Now we have to make some changes to our text image 2D arguments. The image is 500 by 300. And that works, but it's upside down. And you know what? Our pixel image was upside down this entire time too. Our first pixel was white, but it's on the bottom row. This is actually to be expected. Whenever we think of image files, the origin, where we find the first pixel of data, is at the top of the image, while in WebGL the origin is at the bottom. So we have to flip things. We could flip our UV texture coordinates. We could also modify the image in an image editing program, which is actually a pretty common strategy. But the easiest way to do this right now is to change the pixel storage setting before we call text image 2D, like this. Okay, so let's take a closer look at that function, textImage2D. In WebGL, this function has 13 different forms. It looks confusing at first, but it's really not. The first thing to notice is that all 13 functions share most of their arguments. They all take essentially this form, where only the last argument, the source, varies. And width, height, and border are sometimes optional. In these cases, you can either supply a width, height, and border, or you can leave all three out. So let's go through these arguments then. Target is texture 2D. In this case, it could also be one of the texture cube map targets, but I won't be going into this here. Level is only useful for MIP maps. Typically, this value will be 0, though if you ever choose to define your own MIP maps, this value will be 0, and then 1, and then 2, and so on, up to a maximum of 12 for the very largest texture images, I think. Anyway, if you aren't using MIP maps, or you're choosing to let WebGL generate your MIP maps for you, this value should be 0. Internal format is used to describe the colors of the final texture, that is, the texture used by your fragment shader. This typically is either RGB or RGBA, but it could also be a luminance or alpha value. Width and height are the dimensions of the source image. You must provide this if your pixel data is coming from an array or a buffer object, basically anything that doesn't have an intrinsic size that the browser can figure out on its own. Otherwise, these values are optional. If your width and height are smaller than your image dimensions, then WebGL will trim away the pixels furthest from the origin. And if your width and height are larger than your image dimensions, the entire function will fail and your texture won't get uploaded. Border is always 0. If you pass any value other than 0, you'll get an error. Format and type describe the source pixel data. Typically, this will be something basic like RGBA and unsigned byte. But WebGL allows a huge number of fairly sophisticated bit packing strategies. For example, expressing RGBA color values with 4 bits instead of 8, or RGB color values with 5 and 6 bits. It's pretty interesting what combinations you can get up to here, but if you're using a JPEG or PNG image for your texture image, then you're stuck with RGBA and unsigned byte. Last, there is the source. If you look at the documentation, there are 7 unique data types that you can use here, but when I look at these, I really just see 2 or 3. First, your source can be an HTML element. This might be an image element, either one that's on the page already or one that's not been added to the document tree. It could be the contents of a canvas element. It could come from a running video. It could also be part of an image that you've extracted using create image bitmap. And as I just explained, it's up to you whether to use width, height, and border in these cases. Second, you can create your own data array using any of these JavaScript typed arrays, just like we've done already today. Something interesting here is that you can also provide an offset value to skip over certain values in the array. The third one is really a slight variation of the previous type. In place of the source data, you give an offset, which could be 0. Where does your pixel data go? Well, instead of providing the data directly to TextImage2D, you put the data into its own buffer. Remember how we used array buffer to store vertex data and element array buffer to store index data? Well, we can use pixel unpack buffer for our texture pixel data. This isn't really the purpose of pixel buffers, but if you've ever wondered what this overload was for, that's it. So I hope that that explains everything, except just one more thing. Let's go back to our fragment shader. So we declared a uniform, but if I remember correctly, we never set a uniform value. We never even looked up a uniform location. Is this sampler empty? Is it not actually necessary? If so, how is our program working at all? Okay, so this is interesting because it teaches us something about both textures and uniforms. Whenever you declare a uniform and use it in your fragment shader, but you don't set a value in your JavaScript, it still gets a value. It gets a default value. If you declare a vec4 for, say, an RGBA color, it doesn't just come filled with zeros, it comes with 3 zeros and a 1. In the case of an RGBA, that means RGB would be 0, so the color black, and the A, the alpha, would be 1, so fully opaque. If you declare a mat4, you won't get 16 zeros, you'll get an identity matrix, which looks like this. If you declare a float or an int, you'll get 0, and if you declare a sampler without setting anything in JavaScript, you'll get the default texture unit, which is always texture 0. Okay, so then what are texture units? Well, instead of answering this question directly, let's ask a different question. What happens if we have more than one texture image in our program? Say we want to blend 2 images at once. Thankfully, WebGL allows us to upload multiple texture images and use multiple texture images at the same time in our shaders. And that's what texture units are for. It's WebGL's way of letting you keep track of the different texture images that you want to use in your application. The number of texture units you can have is not unlimited, and the exact number varies, not by browser, but by hardware. It's a GPU limitation. My crappy Android phone allows 96, my 8-year-old Mac allows 80. Currently, I think WebGL guarantees you at least 32 total texture units. So those are texture units that you're allowed to upload to, but there's an additional limitation, and that's the number of textures or samplers you can have in one shader. Currently, I believe WebGL guarantees you at least 16 texture units per shader. Your system may allow many, many more. If you plan on using a lot of textures, then you're going to need to figure out what every user's computer is capable of. You can do this using these 2 lookups. Right, so now we understand what's going on with texture units. How do we handle this in our code? It's actually pretty easy. Before binding a texture or modifying its data, you need to decide on an available texture unit, basically a number. This is the value you decide. For smaller applications, you can probably just hard code your values as you require them. And if you have a very large application with many textures, or if you're writing a library, you may want to build a system for managing your texture units and recycling texture units that aren't needed any longer. First, in your shaders, you'll need to declare a uniform sampler for each texture you need. And you'll need to use them. One way is to simply multiply them, but it all depends on what you're actually trying to achieve. Next, your JavaScript. During initialization, you'll want to look up the locations of these uniforms. If you've decided on a texture unit value, you'll probably want to set the uniform values here as well. Note that for uniforms, the texture unit value is just a number, like 0 or 1 or 15. Then, when you have image data ready to upload, first you activate the texture unit. Here, though, you don't just use a number like you did with uniform. No. You have to specify it using either the named texture unit, like texture 0 or texture 1 or texture 15, or by adding the value in texture 0 to the texture unit number that you want to use. Both strategies will actually give you the exact same value. I know this seems weird, but it's just the way that you have to do it. Next, you bind your texture. If you need to flip your image, you can call pixel store I, like you did before. You may want to undo this later if you have other images that don't need flipping. Then call textImage2D. Then deal with your mipmaps the way that you want and set any texture parameters that you need to. Do that for every texture until you're done. Then, whenever you make your draw call, your textures are ready to go. So that's a lot to go through. I recommend that you download the code and experiment with it yourself. As I said at the beginning, this is not an advanced skill, but there's still a lot to take in here, and I recommend that you practice a bit before you start building any large applications using textures. I really hope that this all makes sense.